I would like to get this session started. I'm Lydia Kavraki from Rice University, and I will be chairing the session. Our plenary speaker today is Dr. Carme Torras, and Dr. Torras is a research professor at the Spanish Scientific Research Council. She received her master's degrees in mathematics and computer science from the Universitat de Barcelona and from the University of Massachusetts, respectively, and she got her PhD in computer science from the Technical University of Catalonia. She is a member of the Academia Europea and a member of the Real Academia de Ciencias y Artes de Barcelona. Many of us know Dr. Torras as her role as an editor of, in her role as an editor of the IEEE transactions on robotics. I was impressed when I went to Dr. Torras' website. She's a very prolific researcher whose interests span robotics and AI. She has done extensive work in perception and action in robotics, learning and adaptive systems, constraint satisfaction, computer vision, robot motion, and robot manipulation, including manipulation of deformable objects. So please join me in welcoming Dr. Torras.
Thank you, Lydia, for this kind introduction, which I'm not sure to deserve, but it feels good. Before starting with the subject of my talk, I like to say that I work at the Institute of Robotics in Barcelona. That depends on the Council of Scientific Research of Spain and the Technical University of Barcelona. We are about 100 people there, researchers working, and one of our main task forces are robots. We have legged robots, wheeled robots, parallel platforms, small humanoids, and we even have, as you see in the center of the image, a robot in the shape of a soccer ball that has 12 linear actuators that permit it rolling in any direction. This was designed to help our favorite soccer team, which is Barça, when they got in trouble. But because we are very near, we are 500 meters from the stadium. But as you see, they don't need our help because they are now in the final of the Champions League. In particular, my research group works or runs the Perception and Manipulation Lab, where our goal is to place manipulators in human environments. We do work at the frontier of robotics and AI, combining perception, learning, and planning. Therefore, we are very much in line with the 50th anniversary celebration of Shakey's project that tries precisely to join back AI and robotic fields. Now, entering the subject of my talk, textile objects are all around us in human environments, and their versatile manipulation would open up many possibilities, from housekeeping and hospital logistics to automation in the clothing and internet business, to help the elderly and disabled to be more autonomous. This, however, poses many challenges because it's very much harder to manipulate and perceive deformable objects than rigid objects. And I have grouped the challenges for learning algorithms in 5 categories. The first is vision learning for garment recognition and post-estimation, usually using rgb-d data. The next one is motion learning for skill tuning. Safety issues are crucial when manipulators are placed near people in physical interaction. Moreover, human-robot collaboration, as we will see, can be learned through demonstration. And finally, cognitive learning, meaning learning to plan, is important in order to get a sequence of skills. Starting for the first topic, namely garment recognition and post-estimation, we have an approach that we call informed grasping. What do we mean by informed grasping? When you like to perceive and determine the pose of a piece of clothing, the usual way is to do a lot of regrasping in order to get it to a standard configuration. This, of course, eases perception a lot, but may be very slow. Therefore, we have an alternative approach that is trying to do just one-shot grasping. And for this, we use more involved computer vision and machine learning algorithms. This one-shot grasping is intended to perform a task, and thus it has to be, the grasping has to be in a particular part of the garment. We have built a clothing data set with labeled parts, because as I said, informed grasping requires grasping it by a given part, for instance, the collar, in order to hang a garment. We have this data set in which we have labeled the collars, the hips and the hemlines of pants, the cuffs of the sleeves of shirts, and for each clothing item, we have not just the annotated color image, but also a template for background subtraction and a depth image. This is publicly available in our website. Then we have devised a pipeline, a vision pipeline, that starting from rgb-d and depth image, in a training phase, we compute descriptors by sliding a window along the image, and then we build a dictionary of code words using a back of words approach, and with a support vector machine, we classify the different parts as a training set. And then in execution, we compute the descriptors again to build this probability map of having a collar that you see in the middle of the image. Then we place a box around the most probable place where a collar can be located and find the best grasping point, apply another technique. I will show this in a video. The task here is from a pile of clothing to detect a collar so as to hang it. Let's see. You will see our setup consists of one robot arm and a Kinect camera, and that gets a color and a depth image, and we like to detect the color. For this, as I said, in execution, we, through a sliding window approach, compute the descriptor for every superpixel that gives this map of likelihood of having a color. Then we fit a box in the most likely place, and then there we compute the most suitable grasping point, using basically the depth image to compute the grasping point in the lapel. Then in the grasping, you'll see that our robot uses a homemade parallel jaw gripper to detect to grasp by the color. And what is most important is to have detected the whole of the color so that the hanging is successful, and as it is here, as you see. Well, the same pipeline has been used in a mobile manipulation context in which we have this vehicle on which the one arm is mounted, and then we use this laser that you see on top in order to navigate toward the target. This is the image got through the laser. It navigates to the target, and then a Kinect camera mounted on the robot arm does the same processing as before in order to detect the color and pick it up. Sorry, I shouldn't have said that. Our robot has such predilection for colors that sometimes it scares and worries students, as you see. Oh, no, I have to go here. We have not only used descriptors, as I mentioned, in the pipeline, but we are now using also these deep learning descriptors that are very fashionable nowadays in order to segment clothes worn by people. For this, of course, we need a large image database of people dressed. Now, so far I have just talked about recognition, be it of clothing parts or entire garments. Determining the pose of clothing is a much more involved problem. It requires not just classifying, but also determining shape, which has an infinite dimensional space. And this is usually accomplished by matching points between a reference image of a reference position of the clothing, in this case a t-shirt on the left, with a current deformed pose of the same shirt. We have developed a descriptor called DALI for deformation and line invariant descriptor, which has shown to outperform state-of-the-art descriptors such as SIF and DAISY, as will be seen in this image. We have also collected a database of piece of clothing, and we have compared all these descriptors. And you see that DALI outperformed all of them, DAISY coming very close. This work is now being published in the International Journal of Computer Vision. Once we have 2D, 3D correspondences, it is possible to track the pose of clothes, as shown here for this t-shirt. However, this is only possible if deformations are very mild, as here. So this can be traced in real time. But in order to fold clothes or manipulate them, we have to cope with much stronger deformations. But as a counterpart, as a good counterpart, we do not need high precision, as required for rendering in computer graphics, for example. Therefore, we seek simple, qualitative models that encode task-relevant features. And as future work, we plan to combine the features obtained by learning descriptors, such as those I have shown before, with structure provided by computational topology constructs, graphs of parts, etc. This is our future work in the visual learning field. Coming to the next challenge, namely motion learning, we have tackled it by tuning manipulation skills through reinforcement learning. In particular, learning to fold a polo shirt by coordinating the motion of two warm arms. The approach starts on the left by guiding the robot to perform a desired motion, which is the initial demonstration. This is then represented as a parameterized trajectory, in our case, using dynamic movement primitives. The parameters of these are the weights of the Gaussians. Then, in a next step, the robot optimizes the trajectory in the parameter space by searching in the parameter space using a cost function that encodes a measure of task success, the ergonomics of the robot, safety, etc. I will show an example, which is learning to fold a polo shirt with two warm arms, which is a quite difficult task even for people to perform. So you will see that some people really have trouble doing this task with two hands, while others perform it neatly. He actually is the work of Adrien Colomé, who is this guy that now teaches the robot to perform the task. And then, with a zenithal view, you will see how the cost function keeps improving. What is the cost function here? The cost function is that the polo shirt has to fit a rectangle. So all the things that get out of the rectangle increase the cost. So you see that through repeated execution by itself, the robot reduces the cost of the task. As you know, reinforcement learning has a problem that the high dimensionality makes it very costly to do all this search in parameter space. So we have devised several procedures to reduce the dimensionality of the search space, namely the parameter space, by searching only along relevant directions, by introducing a second layer of Gaussians. So the first layer is freezed to the first demonstration, and then the search in the parameter space is just done in a fewer set of Gaussians. And as future work, we plan to reduce the coordination matrix by exploiting that many degrees of freedom in this task are coupled, so they do not need to be treated independently. Turning to the next subject, challenge, which is safety. This is especially crucial in applications that require physical interaction with people, such as, for instance, helping to dress, which is one of our target applications. For this, we have developed a parameterized model of robot dynamics whose parameters can be tailored to each robot arm. And this work has been presented in a session today, a few hours ago. We exemplify this in a task that is placing a scarf around the neck of a mannequin and afterwards of a person. In this three-frame video, on the left, you will see the initial demonstration, which is very simple, just guiding the robot to perform the task. In the middle is the rehearsal of the robot in order to improve the motion. And on the right, which is now black, is the most interesting frame you should look at, because as you see, the person can disturb the trajectory of the robot, and the robot behaves kindly to the person, very compliantly, but he persistently continues doing his task. And you see that this person who is in charge of this work, risked his neck. So he trusts the robot a lot. As future work in this field, safety, we like to distinguish between 3 types of contacts. One are accidental contacts, disruptive, as the ones I've shown in the video, but there are other types of contacts that are part of the task. For instance, if we try to put a shirt on a person, it can happen, we are now working on this problem, it can happen that the sleeve gets stuck in the elbow, and then a different DMP needs to be applied. So it's not the same skill, but a change of skill is required. So this has to be taken into account. And also, another type of forces that should be distinguished are those guiding collaboration, that this will show up later in the talk. So coming to human-robot collaboration, we teach through learning by demonstration to teach a robot, in this case, not to dress, but to be like a third hand in assembling a wooden table, namely, for instance, an IKEA table. For this, as perception, we use vision and forces. There are some markers in the top of the legs to be assembled, and the forces are sensed in the articulations of the robot. And as learning algorithms, we use task parameterized Gaussian mixture models in order to encode the motions, the demonstrated motions, and we have formulated stiffness estimation as a convex optimization problem, guaranteeing in this way optimal stiffness gain matrices. This work has been done in collaboration with the Istituto Italiano di Tecnologia, the group of Sylvain Calinon. You see the person on the right is acting as a teacher for the robot, and he makes the robot behave compliantly, while the person on the left is trying to move the board to a comfortable position for him. And as soon as he starts screwing the leg, the teacher keeps the robot stiff for it to learn that it has to behave this way. Then, in the reproduction phase, when the user tries to put the board in a comfortable position for him to assemble the table, the robot behaves compliantly, and as soon as he starts screwing the leg, it changes mode to a stiff behavior. On the top of the leg, you've seen some markers. So when the user is trying to assemble the leg in a bad position, for instance, now in the middle of the board, the robot doesn't recognize that this is a screwing position and behaves compliantly. And the same if the user tries to screw the leg upside down. So we have implemented this work for rigid objects, as you see, but our future work, our aim, is to apply a similar approach to dressing a scenario. Moving to cognitive learning, learning to plan, so far I have only considered learning individual skills. But to accomplish a task, namely dressing, usually a sequence of skills needs to be applied. For this, we need planning, because in a new scenario, you need to be able to sequence several skills. And for this, we have extended the Rex reinforcement learning algorithm to include the human in the loop, so as to speed up learning. So the system we have developed, and that is to be published in the Artificial Intelligence Journal this year, extends relational reinforcement learning with an initial demonstration, because the system starts from scratch. Then, from these initial demonstrations, some rules probabilistic rules are extracted, and through execution, the outcome probabilities of each action are updated. And as soon as the system faces a new situation that it has not encountered before, it requests teacher help. But not just help and nothing else. It guides the teacher of what action or new state he should supply. So it explains why it cannot find a plan and provides hints which in the artificial intelligence literature, in the planning literature, are called excuses. So that, for instance, points to a useful state from which the planner could take on and continue. As I said, as future work, we plan to transfer this to the clothing domain. I can help saying that I like to acknowledge the great support I get from my research group, of which I'm really proud. As we can see, we form a very cohesive team, and we maintain close ties with our robots, which, as you see, persist in their predilection for colors. And before ending the presentation, you may be wondering, where does this illustration come from? Well, working with robotic assistants, or on robotic assistants, I became very concerned about the social and ethical implications of our research. And in a collaboration with the humanities department, I became aware of the serious methodological difficulties involved in predicting technological evolution, not just robotical evolution, any evolution, because new uses of devices appear that had not been foreseen before. And we do not have a language to express what will happen in the future. So I listened to a very provocative talk given by Neil Stephenson, a great science fiction writer, on innovation starvation, where he claimed that the imagination of scientists had dried out after the big projects of space exploration and the development of the microprocessor. So he advocated that we scientists should recur to science fiction writers to figure out innovations and, above all, to come up with plausible scenarios for the future. Because if we cannot predict where technology will lead us, at least we can imagine or foresee several different scenarios and try to orient research towards those that we like. So I didn't want to emulate this science fiction writer, but I took the challenge of imagining our robot assistants integrated into people's lives, with its good and bad consequences. So I wrote this science fiction novel called The Sentimental Mutation, which has appeared in Catalan and Spanish, and I would very much like to see it in English. Its leitmotif is a quotation from the philosopher Robert Solomon, who said, "It is the relationships that we have constructed which in turn shape us." He meant our parents, our teachers, our friends, so human relationships. But if we are to live with robot companions, robot butlers, robot nannies, this can also be applied to robots, since they are going to shape the way we are going to be and our future generations are going to be. So we better choose for what type of robots we like to be modeled. Thank you very much.
Thank you very much for sharing both your technical contributions, but also your thoughts about the vision of about what robotics may lead us to and where we can lead robotics. We can take one or two questions from the audience. All right? Yes, it would be easier if you use the microphone.
Hello, my question relates to the very first video when you were showing the robot grasping from the pile and then hanging on the thingy. I'm wondering if the robot has knowledge where it holds the piece of the clothes, or if it was just coincidence that it held it right here and was able to nicely put it there.
Well, the thing is that we detect with descriptors the hole of the collar. And then we put a box and we detect the lapel, because this is a polo shirt. So we try to grasp it by the end part, the back part of the collar, where we have somehow detected the lapel. I think it's a, yeah.
Okay, thank you.
We have a question in the back. If you can move to the mic, it would be helpful. Thank you.
So I'm just wondering, you say in the reinforcement learning part that when it is not the same as what it has learned, it will then ask the user to guide it again. So how do you decide when the robot should ask the user again? Is it exactly different, or if it is not exactly different, then what is the metric that you use?
The planner has a set of rules that have been learned from the initial demonstration.
Right.
But it can happen that the environment, for instance, let's picture an assembly task in which you have to put several bolts and work pieces in a given order.
Right.
Imagine that something that had to be inserted before is not in place, and a plate is on top. So then the planner cannot find a sequence of actions to complete the plan. So it says, I cannot complete the plan because I do not have any action that can go from this state to this other state. And then the user is supposed to teach how to remove this piece, introducing a new action, which is removing, in order for the system to be able to insert the bolt and then this plate on top.
Okay, so you're not doing any prediction whether this is going to fail or not. It's just when it fails, then you just ask the user.
Yeah.
Okay.
When there is no plan, when it cannot find a plan, it asks.
Okay.
Explaining what the problem is.
Yep. Okay, thank you.
That's the thing.
Do we have another question from the audience? Yes, please.
This is great to see all your progress in this area, and we keep hearing about the increasing elder population who will need robots to help them get dressed. And I'm wondering, you've given this a lot of thought, I'm sure, what are the next steps, or what more do we need to achieve that? I can imagine some better perception, understanding of human kinematics, the topology of clothing, and so forth. Can you comment on that, please?
Yeah. Well, there are many open challenges yet, still. One is to detect the abilities of the user, because if you like to help to dress someone that doesn't have any disability, or one that has some problems of mobility, this should be assessed through vision or force, and it's an open problem. And also determining the pose of clothing as it is placed on the person, it's very hard, because I don't know if you were asking about this or other possible challenges. I see, as I said, I grouped in 5 categories the challenges, because there are vision challenges, motion, force control challenges, safety challenges, interaction and understanding the intention of the user, for instance, distinguishing when it is trying to collaborate from where it is trying to avoid that the robot gets on him, and also more cognitive challenges of being able to face new situations and plan motions that had not been demonstrated before. So it's a whole range of challenges that we are facing.
Yeah, it is a huge topic indeed, and I'm going to stop you here because we are running out of time. Please join me in thanking Dr. Torras again.